Alright, pre-AP kiddos, this is the last of the acid-base notes, so I think this is the 5th video on acids and bases. It's talking about titration. These are the old book page numbers. The chapters are 14 and 15 if you're in the new textbook, I'm pretty sure. So, titration is just a neutralization reaction. So we talked about anytime you have a reaction between an acid and base, the products are exactly the same. They are salt and water. And so some kind of ionic compound, any ionic compound is a salt, and then water is the other one. It says neutralization occurs when hydronium ions and hydroxide ions are supplied in equal numbers by reactants. So we're going to have an acid and a base, and usually you have an acid sitting down in a container or a base sitting down in a container, and then the opposite is dripped down into that container until we reach this neutralization point. So still back to, and we've already talked about this, acids and bases reacting to produce salts and waters. So it gives us a couple little examples here of neutralization reactions. This is the one that we normally do a titration of in class, where we take hydrochloric acid and we take a strong acid, and we take sodium hydroxide, a strong base, and we mix them together, and when we do, we get neutral salt out of it. So we get a salt, sodium chloride, and water. This one gives us another equation. I kind of skip right through this when we talk in class because the math becomes much more difficult when we're doing weak acids and weak bases, but same idea. This is acetic acid with sodium hydroxide. We still form an ionic compound, so this is still a salt, it's just sodium acetate, and then water. I'm not going to get into the details of why this salt is basic today, but if you sign up for AP, you'll know more than you want next year about it. So salts can be neutral, acidic, or basic. All the ones we would deal with in class and all the ones you're going to deal with on worksheets are going to end up being neutral salts. So this is what a titration setup looks like. Yada yada yada, doesn't matter. So you get, what you have here is some kind of stand, a titration stand with a burette. There's a tube right here, and that tube is filled with what they refer to as a standard solution. The definition of standard solution is on the next little slide here. And so standard solution is the one you know the concentration of. So you fill this whole long, really accurate tube with that standard solution, and then in the flask, I don't know if you can see it down here, in the flask down here you put the unknown solution. When they say unknown solution, you know what the solution is, you just don't know what the concentration is. This is all about figuring out, I know the concentration of one of them, how can I use that to find the concentration of the other? So let's just pretend here that we're trying to figure out what our acid concentration is. So we're looking for acid molarity. That means we would know up here the base molarity. That would be our known. Hopefully you can see that. And so what would happen is we would put a certain volume of acid in here with a certain concentration. Acids are clear. We would put it under the burette, and we would add something called an indicator that would make it change colors. So indicators turn different colors based on pH. So the go-to one, we were going to use phenolphthalein, which is a clear indicator when the solution's acidic. When it turns basic, it turns hot pink. And so what we would do is we would put this acid flask under the burette, and we would add base until that container turned a light pink. Clear would be acidic, hot pink would be basic. So when it turned light pink, that means we would have an equal number of moles of acid and base in that container. And so if we knew the concentration of the base and we knew the volume of the base, we've talked about this before, molarity times liters gives us moles. And so if we knew the molarity and how much volume we put in, we know how many moles we have. If we have the acid down here and we know what volume we put in, these number of moles for the base would be equivalent to the number of moles of the acid, and we can then divide by the volume of the acid that we put in, and that would tell us the concentration of the acid. So that's the basic idea of titration. No pun intended there. We'll do a couple calculations here in a second. So here's the official definition. This is a method where we use a standard solution and we determine the concentration of another solution. And so the standard solution, that's not a terrible definition, that's the one we know the concentration of. What we're looking for in any titration is what we call an equivalence point. The equivalence point is the point at which the acidic and the basic particles are equal to each other. That's usually where you have an indicator changing color. For us this year, it was all going to be, that's when the indicator changes color. So the end point and the equivalence point for us would have been exactly the same. But there are indicators that change colors at all different pHs, and so technically they're not the same thing. But if your indicator is changing at the end point, then those would be the same. So equivalence point, where you have equivalent numbers of, isn't that nice, where you have equivalent numbers of hydroniums and hydroxides. The end point is which point the indicator changes color. This is a great little graph showing you how this works. When in this case we started with something acidic because the pH is really low down here. Let me see. We started with something acidic because the pH is really low down here. And as you're adding base, it's staying acidic and staying acidic and staying acidic for the first 48 milliliters of base that we add. And then once it hits 50, once it hits that equivalent point, the pH jumps really quickly. It's a hard little point to find. And then after that, we had 51 mils, all of a sudden we're really basic. So lots of times it's really tough to find the equivalence point in a titration. It takes a little practice using the equipment. So anyway, that's our equivalence point or end point there. And so we're going to do a couple of calculations. You'll have a couple of calculations on the worksheet that you will be doing this week and next. So this is it. Titration is what I refer to as MVN equals MVN, where M is molarity, V is volume, and then the N is the number of hydrogen ions in the acid or the number of hydroxide ions in the base. Where ultimately molarity times volume equals moles. We're trying to find the place where moles of hydronium are equivalent to moles of hydroxide. These are maybe the easiest calculations that we do all year. So we'll roll through a couple of them. It should be quick for us, and hopefully you'll get a hold of them pretty quick on your own. So here is problem number one. Problem number one says 42.5 milliliters of 1.3 molar KOH are required to neutralize 50 mils of that sulfuric acid. Find the molarity of the sulfuric acid. Every one of these problems is going to be an MVN equals MVM problem. It's arbitrary which side you decide to put the acid on and which side you decide to put the base on. I always just put the acid stuff on the left and the base stuff on the right. It's one less thing for me to think about, and so I don't care whether you want the acid stuff always on the right and the base on the left because your thug life or whatever, you like to live on the edge or whatever. Doesn't matter to me. But here we go. That is your generic formula, and then we get to plug in the numbers that we know. So do we have the molarity of the acid? Here you go, find the molarity of the acid of the H2SO4. So our molarity there is our question mark times the volume of the acid. They gave us 50.0 mils of the acid, and then the N is the number of hydrogens that the acid has and the number of hydroxides the base has. So here, this sulfuric acid has 2 hydrogens to give away. And so its N value would be 2. And then we would place that equal to the molarity of the base they gave us. It's 1.3 molar. They gave us the volume of the base, 42.5. Because the base is the known concentration, that would be our standard. It's the one that's going to be in the long glass tube. It's called a burette. And then times the number of hydroxides that are in that base. In this case, we only have 1 hydroxide. You still got to be able to identify, look, the thing that ends with OH is the base. The thing that starts with hydrogen is an acid. And then we are plugging those values into our calculator. You multiply the side with numbers, 1.3 times 42.5 times 1, divided by 2, divided by 50. And when you do that, you get the molarity of the acid, I cheated, is 0.55 molar. That's the concentration of the H2SO4. Looks just like that. Good? I got one more. If you're up for one more. Oh, there's what it looks like if somebody does it nice and pretty. Uno más. That means one more in Hungarian. See if I can get this folded up a little nicer. Squeeze it in here. Alright, here we go. Last one. This one says you have a 15.5 milliliter sample of KOH, acid or base. That should be the base. Solution's mixed with 0.645 molar HCl. That should be our acid. You should be able to name those things. That's hydrochloric acid. In a titration experiment, calculate the volume of the hydrochloric acid. Here we go, generic equation, MVN equals MVN. I always put the acid stuff on the left. This time it gives me the concentration of the acid. So 0.645 molar times the volume of the acid. That's my question mark. What is the volume, or calculate the volume of the acid, times the number of particles. For HCl, we just have 1 hydrogen that's going to be given off or ionized. That will equal the molarity of the base. They gave us 0.215 molar times the volume of the base, the 15.5 milliliters. And by the way, we deal with gas laws, we've got to turn them into liters a lot of times. Because this is this volume over here and this volume, we're talking about a proportion here. If this is in milliliters, that will be in milliliters, and vice versa. So you don't have to convert them to liters. It also means you don't have to convert them out of liters. If this one's liters, that one would be liters. Usually titrations are done in milliliters. And then the number of hydroxides is 1. And so we can calculate our volume of the acid. This one, I don't have the answer here, so I'm going to plug it in really quick. 0.215 times 15.5 times the 1 divided by 0.645 divided by 1, if you're really excited, is 5.2 milliliters. That milliliters went to the tens place. That's a good indicator that sig fig wise this one should go to the tens place, and that would be the volume of the HCl that we needed. That's how titration works. Pretty neat. You got an unknown solution and you can determine its concentration by making up a solution you know the concentration of. That's it in a nutshell. See y'all soon.